Okay.
Talk by Pipo. That will start again the talk right now.
Okay. By the way, the drawing I made it with a PowerPoint. I'm becoming an aficionado. Well, so yes, I was saying the talk has two parts. One that is a little bit go through how one derives Fokker-Planck or Cramer's type equations from Langevin equations. I'm following this paper that is about Langevin equations and relativistic setups, but it has the full derivation that I'm going to show here. I think you may also find interesting in that sense. And then I'm going to talk a little bit about the open phase space quantum dynamics and how one can get equations that they resemble kind of what one see in stochastic processes for open quantum systems. So what is a Langevin equation? We're calling a Langevin equation a system of coupled, possibly nonlinear, but first order linear equations where this Xi here denotes a vector of random variables. This object here is vector valued, of course, and this thing is a matrix over this thing, this gamma, that is going to denote a vector of random variables that describe Gaussian white noise. Okay, Gaussian white noise is a random variable that is Gaussian, that has zero average, and such that the correlations in time for two different times correspond to a delta distribution of the difference. And that is to say that basically the noise is not correlated with itself unless you're measuring at the same time and it has like an infinite covariance. Sorry, variance. We also, well, this is a vector of random variables. We assume that each component of the vector is independent in such a way that the components, if this were like gamma I, gamma j, there will be a delta ij here. So what is the problem with this kind of setup? Well, if you try to integrate this set of equations directly, there's something that you should be able to do. You're going to find that there's some type of time order Dirac deltas. So this is the problem because this object is not well defined, nor even in the sense of distributions. If you're familiar with distribution theory, you can see this kind of integrals as something that has to do with multiplying the Dirac delta by a step function in the same variable. And that object is not well defined. It depends on what the value of the step function is when the jump happens, right? And that has to be further specified. That's one way to look at it. If you know about microlocal analysis, what happens is that the distributions are not comparable and in principle cannot be multiplied. So how do we make sense of these equations then? Because this corresponds to a sensible physical situation, because we have a deterministic force plus something that is introducing noise in the system in a way that depends on the position of the system, and in a way that the correlations of the noise, we assume that, for instance, we have a gas of like particles or whatever is not correlated with itself at different times because it's very chaotic, right? So the way we make sense of it is with this finite difference equation. This finite difference equation is telling us that the random variable varies over a very small time interval with this deterministic force plus this diffusion matrix evaluated at some point within the interval. If we have like a usual differential equations, it wouldn't matter which point we're picking here, because in the limit, when we divide all this expression by delta t, we would get that it does not depend on lambda. Why does depend depend on lambda? Because this object here is the variation of what is called a Wiener process. There is a process that has independent increments. There is Markovian. It's non-stationary, but the idea is that the differences are distributed like a Gaussian distribution with variance that is given by the difference in time, right? So this process stochastically is not differentiable respect to time, and more concretely is not how you call it well, in the sense of the variance, that is like one measure in which one can define differentiability or continuity respect to time in stochastic processes. Once we have this equation, we want to know how these variables, chi, each of them is distributed. So we want a function that depends on the configuration space, that is all the possible values that this chi's here can take. And well, we basically proceed. Forget about what is, just try to follow what I'm saying. Do not look at the whole slide at once. So we want that any observable that we evaluate its average by just applying the integrating against the distribution function f for a very small interval, which is going to be given by this thing, coincides with the variable distributed at a later time delta t. It's like this is like switching between Heisenberg and Schrodinger picture and imposing that they coincide, kind of. If you look at these equations, it's easy to see that you just expand on one side the distribution function, and the other side you expand. There may be typos, but on the other side you just expand the h evaluated at the time t plus delta t given by the equation above. So that gives you kind of like two expressions that have to coincide at the lowest order in delta t. That gives you some expressions that you can integrate respect to the Gaussian white noise. And that gives you, when you compare them, what is called the Kramer's equation. Okay? This is basically telling you that the statistics of the system undergoing the Langevin equation are given by the distribution function whose time derivative is given by this object. It basically can be written as a current too, but I didn't write it here. So you have this term that basically is describing the drift, or how the mean values move around over time. It's basically a deterministic term, plus this thing that is called the diffusion term, that basically is telling us how the variance spreads over time. So this is a characteristic of white noise. When you integrate white noise, you get stuff like this. If this was not white noise, or was like other kind of stochastic process, one would expect to have higher and higher derivatives. Then that would be what is called a Moyal expansion. But with Langevin equations, we get this kind of simple second order, the partial differential equations. Note that for the distribution function, we always have that this equation is linear in f. That's a property that one would expect of a probability distribution function over time, because one should be able to forget, for instance, and create a mixture after the dynamics or before the dynamics and describe the system in the same way, right? Something that you may be familiar with is the particular case when one has just one variable that is sourced by white noise. That's basically going to be the Wiener process or Brownian motion. That gives us what is called the Fokker-Planck equation. there is this object here. There's this equation here. Basically, it's telling us that the spreading of the probability distribution function over time is going to be Gaussian. So some comments. What happens when, well, you can notice here that this lambda, that is basically the point at which we're calculating the finite differences, only plays a role when the diffusion matrix depends on the point, right? When we have that the noise is sorted in a position-dependent way, if you want. So you can see here, for instance, that it doesn't matter. This is like a feature of the Fokker-Planck equation and similar equations, that if you have homogeneity in how the noise acts, then we don't have a problem on the way we define the noise. That is like with this drag delta kind of thing. It will, though, we have this space dependent, if you want, or like a phase space dependent noise. So depending on which value we decide to take for calculating the finite differences, we will get different equations that will give like different results that basically enter here on how the average distribution drifts. So the most, so depending on the area, some people do some things and some people do others. The so-called Ito calculus, it's called calculus because when you define different finite differences in this way, then your changes of variables and your integrals have to be changed accordingly. When you set lambda 0, what you get is something that people use in math and finances because it's easy to handle and because it corresponds to kind of discrete processes, because you're taking only the value of the Gaussian noise at the point in which you're calculating the finite differences, not after. When you get the Stratonovich calculus is when you set lambda to equal to 1/2. This is common in physics because it can be understood as the continuous limit of noise that is called color noise. That is, that depends on the frequency. That is, there's not a delta. It's something like, looks like a delta but widened. Okay. This is the one that I think is more sensible for physics in general, like for whatever thing that you want to do. I don't know what people use the Ito calculus so much. In some cases, people use the post point. That is the, oh no, it's not lambda 0, sorry, it's lambda equal 1. It's more, in this situation corresponds to taking the point here to be the final point, right? So that is cool and is used in some contexts just because it's easy to calculate stationary points. But I've not been able to check the reasoning of why one would choose one over the other in like a more technical detail or like more conceptually clear detail. So, well, this is what I wanted to say about the classical setup. Remember that the idea is that when we describe a system of Langevin equations, what we get is that the whole system can be described by the solutions of this partial differential equation. And now we're going to go to phase space dynamics in quantum systems. Consider a linear symplectic manifold, forget the U here. Basically a system of harmonic oscillators in which the points in the manifold are vectors of this kind, where we have these components and these basis vectors. We associate to one of these, each of these points, an operator. Okay. On this form, this is kind of maybe you've seen Wald. This is kind of what is done there in his book in Quantum Theory in Curved Spacetimes. Where this is just the linear symplectic structure that we're defining there over the linear symplectic manifold. Then we can write the canonical commutation relations just as this. the operators associated with two vectors in the manifold are just proportional to the identity times the imaginary unit and each bar and the simplex structure. You can think, for instance, about if you take X and P, what you get is what you should. So in this context, once we quantize the system with a Fock quantization, etc., we can define the Wigner function as this object here. This is a kind of like a characteristic function. So if we have a probability distribution instead of a density matrix here, this would be the Fourier transform of the probability distribution function, right? And this there would be the inverse Fourier transform of the probability distribution function, of the Fourier transform of the probability distribution function, which would give us the probability distribution function altogether. That is, if long story short, if this was classical, this would be the probability distribution function of the system of differential equations, if you want, or the system of random variables. But it is not, because this is an operator and it is a density matrix. So there are like multiple ways in which one could define something similar, right? Well, this object here, maybe you're not familiar, is this symplectic Fourier transform. It's essentially the same thing as the usual Fourier transform, but it doesn't go from one space of, say, time positions to a space of frequencies. It takes a space onto itself, and those spaces have the same dimensions, kind of, and is its own inverse. The Fourier transform is not its own inverse. So how do we describe the evolution in phase space in this case? Well, we just take the Wigner function of an evolved density matrix, and then we just we know that the evolution of the density matrix is going to be given by the adjoint action of a unitary operator. So we just take the action and make it act over this exponential, also called Weyl operator. If the Hamiltonian happens to be quadratic, and then since we're talking actually about harmonic oscillators, then
Pipo, one quick question. Shouldn't be the power 2n? What are you normalizing it to?
Well, yeah, so the Wigner function is dimensionless, right?
Right, but that should be 2n, then not n, I think.
No, because P times Q is has action units, right?
It's just like in statistical physics.
Sorry, what? Jose, I couldn't hear anything.
It's just like in statistical physics. You have P and Q, and the product is has units of action. So it's n degrees of freedom, 2n variables in the phase space, and n in the exponent when you normalize.
So what my point is that so let's see.
So this object here, this differential, has units of action to the n, because it has n p times q.
I do have an issue with that though, because let me show you something very quickly. Can I show you something related to this?
Yeah, go for it.
I need to share screen. Okay, this is from my notes, from my phase space quantum mechanics notes, because I did compute this normalization factor to match. So if you want the Wigner function, this is generalized Wigner function here.
Yeah.
But of course, the difference that I have is a 2n in here with yours.
Yeah, maybe we messed it up last year.
Well, but then when you take the limit, you need the square in order to recover the Wigner function as usually defined. Look,
well, maybe I think maybe you're not defining the Wigner function in dimensionless, right?
I think I am.
You're not. That's the thing. So you want the average of any phase space observable to be the integral of dp dq times the Wigner function times the observable. So in order for that to be true, the Wigner function has to have units of 1/x to the n.
Perfect. Yeah. Thank you, Bruno. That clarifies.
Although maybe you're right.
But that's what people call the Wigner function, though. So what people call the Wigner function is the one that I say, not the dimensionless one.
Yeah, no, maybe you're right, because now that I think about it, I don't know why you would like to have a dimensionless Wigner function.
That's right. No. The Wigner function is not dimensionless. That's the point. I don't know if Jose is talking, but we don't hear him, though. Whatever he's saying.
Yeah, sure. I forgot that afterwards we were integrating. Yeah, sure.
Right, exactly. No, Bruno hit the nail on the head for the answer.
But I didn't hear what Bruno said. I mean, I didn't understand it well, so that's why I was.
Right.
I asked for him to repeat it.
Jose, you can share again. Just let's keep that in mind. That's not the Wigner function. Yeah, but
okay.
Trivially.
Yeah, my bad. Sorry.
The actual Wigner function is the one Edu showed, right?
Yes, the one I showed is the Wigner function. I mean, I know for sure that one is right, because when I wrote it, I did derive that it corresponds to the ones that it usually used as well. So.
Yeah. Then we want the Wigner function to have units. Yeah.
I think the mistake comes from confusing Wigner function and we are associating it to the probability, to the density of probability, and unconsciously, I think we are associated to the partition function. That is the actual thing that is dimensionless.
Yeah, I agree.
Yeah.
That's why you said it's like in statistical mechanics. All right.
I mean,
no, but I think my mistake was more basic. It was that I was confusing probabilities with probability distributions.
Yeah.
Well, so the idea now is that if we apply this adjoint action of this unitary over this byte operator.
Just saying the last thing, because that I think is important for people to keep in mind. It's true. I mean, a probability distribution will have units, because you want to be dimensionless when you integrate. That's the whole summary of why it has to be dimension full. All right, just keep going. Which is what Bruno said, basically.
Yeah, no, good point. So, yeah, when we act with this unitary over this byte operator here, what we're gonna get is another byte operator. That's what the quadratic Hamiltonian is doing. So, and you can work it out in such a way that you end up getting that the Wigner function over time, evaluated at some point, sigma, sorry, xi, is the Wigner function that you had in the beginning times this object here. There's just a canonical transformation that is basically giving you the solution to the classical equations of motion that you will get with the classical version of this Hamiltonian. Okay? So basically, it's like the Wigner function evolves over time just with the classical pullback, if you want, over phase space of the canonical of the classical evolution. And that's cool, right? So that's telling you that if you have, I don't know, a potential or whatever kind of interaction that you can think about that is quadratic, and you put it on a harmonic oscillator, you just have to displace the initial distribution that you had on phase space according to the classical motion of the oscillators or whatever. So what happens if we have an open system? Well, when we have an open system, we're treating the density matrix of a subsystem AB, just taking the partial trace over the second subsystem, right? Which is then we calculate the Wigner function associated with this reduced density matrix. Well, we get something like this, which we can extend by the properties of the partial trace, something like this. Okay. So this is basically the idea that when you take the average with the whole state over something that is trivial on the subsystem, is like taking the average with the partial state over that observable. Okay. Moreover, if the state is factorized in this way, that is that at time 0 the state is uncorrelated between A and B, what we get is just something like this. And And let's assume further that, for instance, we have that the system B is something like a quantum field, okay, a free quantum field that is quadratically coupled with the classical system that we have at hand. Then this object here, the evolution of these operators associated with the system A, there's the system that we're using as a probe, kind of, and some kind of Andrew DeWitt type coupling, is just given by this thing. It's just the sum of some of the operators associated with the subsystem A plus a smear field operator that depends on the linearly on this initial vector psi prime. So the idea is that this R and this F are describing the classical evolution of the system plus field. Usually we could just like treat this thing as something like this, right? We just like taking the reduced S, but if we don't want the S, if we don't want to treat the quantum field as something that like a vector space that is like has like this Q1, Q2, Q3, whatever, it's better to do it like this. We just like treating it as these operators that we treat in the usual way, plus this field amplitude. Then this is just relating, you can relate everything with the propagators of the field, etc., and it's nice. The idea is that if we start with a factorized state and the evolution is like this, what we get is that the Wigner function associated with the system as time evolves is given by this Fourier transform, where the characteristic function now has factorized in the characteristic function of the field associated with these functions that are basically the field amplitudes sourced by the system, and this characteristic function that is associated with the this R that is given the evolution of the harmonic oscillator as it interacts with the quantum field. All this thing is exact. What happens is that if the state of the field is quasi-free and even, or Gaussian if you want, what's going to happen is that the averages of the Weyl operators are going to be given by Gaussians. And more concretely, we take into account that this F has to be linear because the equations of motion are the classical equations of motion are linear in these parameters psi prime. Then what we get is that this whole thing, this whole characteristic function is just a Gaussian over psi prime. Then what we realize is that then for an open system, what we get is not that we have just the pullback of the classical equations of motion, but we have the convolution of the initial Wigner function of the system with some kernel that depends on t. So the idea now is like, if, for instance, if we didn't have noise, we didn't have the quantum field, what we would have here is just something that is pulling back the classical equations of motion. That is, it would be like a delta function. In this case, it's not a delta function, it's some, let's say, widened version of a delta function, okay? This is the idea now. When we have noise, with the Wigner and a quadratic coupling to a quantum field, or in general to another part of or another linear system of harmonic oscillators, or whatever, what we're gonna get is that the evolution is gonna be given by the pullback of the classical evolution over phase space plus this kind of erasing that is given by the width of this Gaussian. Here I just put R tilde to denote that this is kind of like an adjoint, or like a how you call it, transposed version in the symplectic sense of the evolution, the equations of motion. So now this is something that I'm not gonna do. It seems complicated because you have to use the actual classical equations of motion that I'm not gonna show here, but you can see it on the papers that I've shown. what happens is that you can show from this kernel that the derivative of the Wigner function, the reduced Wigner function, is given by something like this, which is totally determined by the classical solutions that are encoded in R and sigma, and which can be solved numerically with the Laplace transform methods. So we realized that this is exactly the kind of thing that we had before for the classical Langevin equations, only that well, things may happen. These things are not these things are time dependent. In the other case, we were not explicitly assuming that things were time dependent. And a couple of things that may have escaped me while I was doing the analogy, but in general, we have that this thing is a drift term, or like a deterministic term, and this thing is kind of like a noise kernel. It makes sense because these are, it only depends on the position of the harmonic or system of harmonic oscillators, and these sigmas here depend on the action on the field. So from this point, one could expect that one could perform like further approximations, right? Depending on how one calculates these quantities. For instance, one can think about a Born approximation in which these things, this sigma doesn't depend on the state of the detectors or the state of the symplectic system. Or we can just like try to expand all this expression on weak couplings or whatever. But the message is that we actually get something that looks pretty much like a classical equation of motion for a stochastic process. So I hope that this, well, I think this is interesting to see how this works. I couldn't get further with this, but I hope that you enjoyed so far and you could get something out of it. So this is what I wanted to say.
All right. Thank you, people. Questions, people? Questions for people? From the people, for people. So can you go back to with the choice of lambda? I want to understand the Ito calculus things better.
Okay.
No, up. You show me what it does, not the.
Okay. So you have a. Okay, so it said that you start from here, right?
Right.
So this is not well defined because this process is not well defined.
So what I'm confused now.
The gamma, each of the gamma.
Yeah.
Well, this is a vector in which each component is a gamma. These gammas are not well defined as stochastic processes because the correlation factors are like singular, which means that they cannot be time ordered.
Yeah.
So what happens? Imagine now that.
But it is a choice. So my question would be: it is a choice of how you integrate a delta, right? As in, like there are infinite ways in which you can do it. Same speed, as you can consider an ascent delta, go different speeds, go different ways. Right?
Exactly. The Nasser delta thing gives you the Stratonovich calculus.
Right.
Or on nascent deltas that come from that are asymmetric, for instance.
So I have this. So let me show you something to answer the question, to illustrate the question better, because I have used this stuff in the past. Because when you have a delta switching, if you want to do perturbation theory with a delta switching, you have the same ambiguity, right?
Yeah.
And I've done this. For example, in this paper. Let me just share screen and show you. And we argue that the one that makes sense is that one, right? The symmetric one.
Yeah.
Here. Right. Well, I don't need to show you a thing. I mean, the calculation is done. But the one that is, so when you have a delta, you have a time order.
Yeah. I know what you mean. Yeah. So
So what are the other ones, and why do they make sense?
Okay. Well, so when you take the symmetric. So you're that's the sensible one because you're considering that you don't have like more intensity in the interaction from one side than from the other, right?
That's right, exactly right. Yeah, that's the argument.
So you could have something like ratchet, I think it's called.
Yeah, that you allow more one direction than you allow the other somehow.
Yeah, that is like you do like a saw.
So that is funny, right? Because you're taking the limit of infinitely small duration in a way, but then you're saying it comes from something asymmetric, though.
Yeah. So this is the thing with this kind of stuff, that you see the microstructure of whatever you're trying to do, because it's relevant, because the correlations are very intense, right?
So what is the Ito choice? What does it do? So what is the Ito choice?
So the Ito choice is when you put this thing equals 0.
What thing? Sorry.
Here lambda.
Yeah, but what does that mean in terms of understanding the limit with nuts and deltas?
Okay. With nuts and deltas, I think that would be. Okay, let me think. I think that means that this thing is 1.
So
this is kind of like you're taking the delta a little bit delayed from the point.
So it's like the delta is somehow away from the limit of the integral.
Yeah.
That is so it's asymmetric to the back, all the asymmetry to the back, pushing all the asymmetry to the back somehow.
Yeah. It's like ratchet. You're saying that basically all the weight of the function is before the point.
Yeah.
It makes sense when you have discrete processes, though. That's what people say.
Yeah, but why? That's the thing that lost me. How is that a discrete process, though?
According to I don't believe in these things too much. I tried to investigate, and the discussion was or talking about the stuff of finances that didn't make sense to me, or talking about supersymmetry. So I gave up. Okay. But the idea is that you're in this equation, this finite difference equation, you're calculating that the value that is relevant, right, for the diffusion is the value that it had before, not the value that it has after.
Okay.
So that the value at a later time, delta t, you can call this thing an elementary time, is given by the diffusion that time, not the time later. So why was this thing discrete? I think I don't know. I think it's like with discrete process, people calculate this thing as a function of the others, and they assume that everything on this side has to be evaluated at t, right? That say xi of t plus delta t equals something that depends only on the step before, not the step after. Am I making sense?
Yeah. Still, I mean, the discrete thing is a stretch from that, but okay.
Yeah, from the physics point of view, putting in the middle is the one that makes more sense to me.
Agreed. To me, that's the one that makes the sense from the physics point of view. The limit of a very, very short interaction. But then, if you have good reasons to break asymmetry there and capture something else in your distribution, again, you have an infinite limit. Yeah, you can define this limit, whatever. Is that integral still defined when you put the delta at the limit? So you have to decide what you do.
I think there's a way of understanding this. If you put, for instance, when you have a unitary and you have a lot of delta pulses, and the way it decomposes is going to depend on this choice.
Yeah, definitely.
So depending on how you're taking the limit, because if you take a limit with ratchet or whatever, you're going to get a different train of unitaries than if you do the other way around, you know? It may have also, something to do with unitarity. I will have to think about it. But yeah, it plays a role.
All right, thank you. Yep.
No problem.
I think the talk was a little technical in the sense that people may have more questions after they watch the video. I don't know. And everything was straightforward to follow if you understand the notation. But I'm not sure.
Yeah, no, I tried to convey that this guy is kind of like this guy. That was the whole point. And I was trying also to show the techniques that I've been, because when I've been reading the papers by Baylock, Hu, and people like that on the topic, they're impossible.
Yeah, that's it. So that for me is a big challenge. Understanding Veiloghu's papers on detectors.
Yeah.
I don't understand them. I just don't. I gave up. I gave up completely understanding them. So if somebody can explain it to me, but Anastopoulos have worked with those models.
Yeah, I mean, I took this paper is by Anastopoulos, eh?
Right. So
That's what I've been reading.
Is it
So
equally challenging to read his textbook?
was that?
What?
Is it equally challenging to read Veilog's textbook?
I've not read the Veilog's textbook.
Yeah, he has a textbook that does all like all the non-equilibrium QFT stuff, which includes this kind of stuff. His paper is difficult, but I don't know if the textbook was easier.
Yeah, I don't know. I mean, I've only gone through this kind of quantum Brownian motion stuff because it's like a kind of phase space dynamics, but it has a lot of stuff in with the path integrals.
So do you look into the quantum walk? The random walk stuff?
No, not
because in some sense the random walk, like a Brownian motion, falls under a subcategory of random walks, right? Maybe.
well, yeah. So yeah, you can write this equation right here. Wait. You can write all this stuff in terms of random walks. When you consider this thing like being t plus delta t is actually, this is psi n plus 1 minus psi of n equals this. Okay.
I see.
Yeah, that's a good intuition of how this thing of the steps go.
Yeah, because it may be that you have some external like coin flip that does this thing, and you move forward n steps, and then suddenly some probability you move backward a few steps, and I think that's one way to think about it.
Yeah. You see, Eduardo, yeah, I think the thing with if you think of t as n and delta t as so say that the t is n times delta t, right?
Okay.
So then this psi wouldn't have to be defined at t plus lambda because it's a discrete process, right? At n plus lambda, that wouldn't make sense, right?
Yeah.
So when you have a discrete process, it kind of means this. When you take this kind of limits, you know.
It's a particular way of doing it in a discrete process. I can definitely think of other ways of doing it, though.
Yeah. So essentially, if you discretize a lattice and choose to label the lattice by n, then lambda being not an integer is not the way you do this. But you can discretize it any other way, I guess.
Yeah.
Like you can probably even discretize in some other way where the left-hand side of 6, I guess, is a central difference, right?
Yeah. Yeah. Yeah, but I think in the random walk stuff, yeah, I think what happens is that when one considers elementary is this equation, not the continuum limit, and then one calculates a continuum limit because it's easier.
I see. Yeah, I just thought random walk might be an interesting thing to look into along this direction, because there has been, on the lattice QCD side, there has been simple models of confinement based on random walk. So it might be that you can convert some QFT problems into this kind of random walk stuff.
Yeah, but isn't that what they claim they do, though?
Sorry?
Isn't that what the Veilog or Harris maybe claim they do?
No. As in, they might be doing that, which I don't really know. But all I know is that there's a lot more like momentum in the research when it comes to random walk when the QFT is a QCD. I don't know about the ones that Veilog does.
Right.
Well, I mean, so there are things here that don't need exactly to be free theories. Just the coupling has to be quadratic between the detector and. But I don't know. I mean, so yeah, I guess you can take the inverse step of what I've taken in this talk, right? You can start by this equation and get to something that looks like a discrete thing, right? And from there,
what Ericsson has in mind,
but yeah, or maybe there is some way to, I don't know. Is 26 technically count as stochastic calculus?
No, because the W doesn't have to be. Well, it's difficult to tell, right? Because if you don't have higher orders, this is still Gaussian quantum mechanics.
Yeah, I guess that's true.
So in principle, it is, but you can accept that the initial conditions are not the function that you have is not positive definite, for instance.
Yeah, that's fair. That's fair.
So what's going to happen with this kind of stuff is that you can have a negative Wigner function in the beginning, but this kernel is going to erase it on some timescale, right? That's what happens with thermal baths. That's the reason why they break coherence.
Wait, this kernel is positive definite, right?
Yeah, no, because I've chosen a state of the field that is Gaussian.
That's Gaussian. So this is a Gaussian kernel, right?
Yeah, exactly.
Yeah, cool.
This is kind of like an ascent delta that moves around. So it's like something like doing like a coarse graining over. No, not only is pulling back the initial Wigner function over the classical trajectories, but it's also kind of like putting noise by convoluting with a Gaussian. That kind of like that's kind of like a filtering. I mean, I like the picture. I think it's cool.
Yeah, it's just ironic that I saw this only yesterday in data science.
Data science.
Yeah, my friend was asking me her exams about Gaussian kernels and stuff, but it was like about data science in biomedical stuff. But
okay, yeah.
It's funny, but anyway.
Yeah, well, so the thing is that so when you do this stuff classically, right, with this kind of stuff, and you solve them, you usually also get something that looks like a Gaussian kernel. So the both processes are very similar. Okay, so if no one has more questions, maybe I can stop sharing. So more things to look at here is Baylock, Hu, and Harris Anastopoulos do two interesting things with this stuff. One is to write all this stuff down, these stochastic equations, these master equations for the Wigner function. But actually, they also provide the methods to solve approximately the classical equations of motion. Because usually they use as a field a bunch of harmonic oscillators. I don't know why they do that exactly, but because then you can do the kind of things that, for instance, you guys do, right? To solve them numerically. But for late times and stuff like that, you can use something there. Basically, this R and this F are going to be objects that are going to fulfill integral differential equations, right? These equations can be solved by the Laplace transform. Not solved, they can be solved formally, and then you can do approximations on the formal solution. But they kind of give like different stuff that what one would expect.
I still think that I don't understand these models that well. So what they approximate, because my point is, okay, what goes on with the approximations and assumptions?
Yeah, I mean, the thing is that basically you calculate it's like inverting a kernel in frequencies, right? It's like you have to take the inverse Laplace transform is tough because you have to do sums over poles that you don't know exactly, and also through how you call this thing, branch cuts and all that stuff. So those are like difficult complex plane techniques. But yeah, I mean, I myself I've tried to wet my toes on that, but still a little bit green on it. So, but I mean, they claim that they have the full solution, and that they under some basic assumptions they can calculate the stuff. But yeah, I don't know.
But then they get superluminal signaling and stuff like that. So
I think that one may be something else, not the problem of this, of the, how you calculate these things.
Okay, what is that then?
So maybe it's a way in which, because the way you calculate these things, right, seems very naive when you write a bunch of harmonic oscillators, right? Because it's like sums over sines and cosines and stuff. But when you go to the continuum, you need to be careful of which distributions you're taking. Causality depends a lot on how you take these limits, because it depends on which part of the complex plane you're taking the limit, because they are divergent. So you have to choose in which part of the complex plane they're analytical and all that stuff, and you may get something that is zero and non-zero because you're not taking these limits properly. I still have to talk to him about it. Maybe it's something that is escaping me, but I don't trust that thing that they violate causality at this point.
Okay. So maybe they made a mistake, you say?
Yeah, because if you write equations for an entanglement harvesting scenario, these things are not related to each other because they're related classically by the retarded propagator. These things respect to each detector, say. And the retarded propagator is causal. So there cannot be any violation of causality, at least in the sense that we're talking within this model. This model is perfect in that sense. Another thing is if you calculate the solutions to this thing with a Laplace transform that is maybe somehow non-local, you have a problem. Or if you not calculate the propagators, you calculate the propagators with mode sums that you're not summing the proper way or whatever. I have to talk to him. Maybe something escaping me.
Okay.
But I don't trust that this model breaks causality at all. I think it's perfectly compatible. As compatible as the classical equations of motion are.
Okay.
Which the classical equations of motion were just like partial differential equations. What can we say?
All right. Okay. I'm going to stop the recording now then. Unless anybody has any other questions.